Of how you would estimate the thermal conductivity, or like derive Fourier's law from the principles of the kinetic theory of gases. And now I want to go back through and change it up just a little bit. I'm going to change this so that instead of calculating Fourier's law, we're going to calculate Fick's law of diffusion. Turns out there's not a lot that needs to change here. The only thing that needs to change is that I'm no longer interested in the heat flux. I'm interested in the molecular flux, so the number of atoms moving across a fictitious interface per second per meter cubed due to a concentration gradient. So now I'm interested in this thing. Instead of the thermal conductivity. So, basically, let me just go down and give you an idea like how you would change this. So, when we did the calculation of, heat flux through a tiny little element down here, we would just change that so that instead of a heat flux, we're looking for a molecular flux. So then the only thing that changes is that instead of the internal energy density playing the role of the thing being transported, we're literally counting the number of atoms being transported instead. So we'll just change this. All the U's, just change them to N's, or etas. So now the number density is the thing that matters. And go ahead and check units, right? So this is number per meter cubed times meters per second equals number per meter squared per second, which is exactly the units of this thing, numbers per meter squared per second. So everything follows except for all the U's become etas. Eta, 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 d-eta. All the cancellations still happen after you do the Taylor series. All of the averaging works out exactly the same way because the averaging was all based on the geometry of this angle, and that whole argument doesn't change here. So everything is the same at that point, and then basically I just need to rewrite all this stuff. So essentially what you find is that, actually, I don't even know if I need to rewrite it. So J double prime equals minus 1/3 V, average value of V, times L. Let's see, the 1/3 comes from the geometry, and that's it. That's basically the whole thing. D eta dz. So this thing is apparently the Fickian diffusion rate, 1/3 average V times average L, which I can actually turn into some materials properties. So that would be like 1/3 times V. So V is what, square root of 8 over pi times kBt over m. So that's V, and then L was just 1 over eta times sigma. And so in this calculation, the pressure does matter, right? So eta does figure into Fickian diffusion. So anyway, so that's one thing that's different. So if I use the ideal gas law, I can replace eta with, so eta is just pressure divided by kBt, and so if I replace that in here, I can actually write the whole thing in terms of molecular diffusivity being a function of pressure and temperature and mass. And so we can derive the Fickian diffusion law this way, and it's really not much of a stretch to do it also for viscosity. So I'll do that in a separate video now as well.